Hello students, and welcome to part 6 of our video series. This week we're going to be going over simple circuits, or simple electrical circuits. So if you remember from the last few weeks, I told you we're starting to move into more applications of physics. So for the last two labs, we talked about Ohm's law and resistance and resistivity, and of course you've seen the ideas of Ohm's law, and I started showing you the ideas of the simple working physical principles of a circuit, where we have voltage, current, and resistance. So you should have a pretty good understanding of that. So I'm just going to kind of jump into it today because we have a lot to cover. Because just in case you haven't seen it in your lecture, I just want to go over how to solve circuits. So this lab and next lab, as far as mathematically, I consider to be the most hardest. For your quiz, please watch this video. And for your lab write-up, please watch this video as well, because I'm going to show you guys how to solve the circuits. And the circuits that I'm going to be showing y'all today is going to be pretty much the exact same circuits that you're going to be doing. So please, you must solve them in the way that I'm going to show you in order to get credit. So to start, we're going to be talking about different types of circuits. So we're going to learn about series circuits and parallel circuits. Like I said before, we know the basic principles of the circuits. You have your power supply or your electric potential. It's going through a wire, so you have some current, some amperage going through. And then you have the resistance. So what we kind of want to know about these simple circuits is basically what's happening at different locations, right? So we might ask ourselves, what is the current at resistor 1? Like, what is the flow of electrons going through resistor 1? What's the flow of electrons going through resistor 2, and so forth? So that's something that we might want to know in an engineering setting. Another thing that we might want to know is like, what is the voltages on each resistor? So what is the voltage on resistor 1? What is the voltage on resistor 2, or the electric potential? And what is the voltage on resistor 3? So those are the two main things that we want to know. So of course this is a fairly simple circuit, so we're going to be starting off with a series circuit. But we're going to need to know how to look at these circuits and learn how to fill out these tables on what's going on for each resistor. So to start, I'm going to just give you some basic facts. So when you have a simple series circuit, the current, remember current is the flow of electrons, right, given in coulombs per second when it's measured in amps. So the current flowing through the circuit in a series circuit is going to be constant, meaning that if the electrons are flowing at 5 amps here, when it gets through this resistor, it's going to be 5 amps. It's going to be flowing at 5 amps here and 5 amps here. It's going to be flowing at 5 amps everywhere for a series circuit. So current is constant in a series circuit. Now, this is something worth noting too. The voltage will be different across each resistor. So here we have 5 volts, right? It's going to follow Ohm's law. Remember, we talked about V equals IR. But the voltage is going to be different depending on what resistor you have. I'll give more examples, so I'm going to actually work this one out in a little bit. But basically what we're going to say is that we're going to have some voltage here, and some voltage here. In this case, I think the solution is this is going to be 2 volts, this is going to be 1 volt, and so forth. So one of the things I want to point out, though, is when you have a simple series circuit like that, we're following the laws of conservation of energy. So when you calculate your voltages, it should add up to your battery, right? Because it shouldn't violate the laws of conservation of energy. In next week's lab, we're going to be talking about Kirchhoff's law, and we're going to, so this is just an early window into the loop rule, just to point that out, and I'll point that out again. Another thing is we're going to have to simplify these circuits, and it's going to become more apparent when we do these examples, but the resistors must add normally. So we'll add this normally. So that's basically some things that we need to point out about a series circuit. Now for a parallel circuit, it's going to kind of behave a little differently, okay? So in a parallel circuit, our voltage is going to be the same across each resistor. So in this example, we have 5 volts here. So the voltage potential here will be 5 volts, 5 volts, and 5 volts. So the voltage is going to be the same and in a parallel circuit across the resistor. Now, the current will be different. So you can think of current like, water flowing through a pipe, right? So you have water going around. It's going to some of the water is going to go this way, some of the water is going to go that way, and depending on the resistance, or you could think of that little diagram of the guy, right? These resistors are slowing the things down. The currents are going to be different. Now, one of the things I want to point out is these little spots right here in a parallel circuit are called junctions. Next week, we're going to learn about the junction rule, and you'll see it when I work an example out. But your currents should add up to the main current out here. So it's known as the junction rule. It'll become more apparent when I show you some more examples. And then one of the things that we need to point out, though, is that our resistors, or when we're adding resistance to get to our simplest form of our circuit, it has to add using this rule, right? It's going to add 1 over your resistance plus 1 over your other resistance, and after you add everything up, you're going to raise everything up to the -1. So that's what we're going to have to do. So now I'm going to start with example 1. So when you're doing these, they're going to give you a diagram. So the first thing that we're going to do, and of course they draw them for you, but you're going to draw it yourself, is we're going to have to draw these circuits. So for your lab reports, you could use the software to draw the circuits, but you must draw your circuits. That way you understand what's going on. But the step 1 that we're going to do is we're going to draw the circuits, and we're going to go straight to our table, and we're going to label everything that we know about our circuit before we do anything, okay? So step 1 is draw and label our tables. So right here we have resistor 1, resistor 2, and a resistor 3. We're going to label that in our table under our resistance. And then we're going to ask ourselves, what else do we know? Well, we know that we're working with 5 volts. So we're going to try to get to our simplest form of our circuit, and that's known as the equivalent circuit. This is why this is an EQ. And when you look at this, whatever power supply that you're using, this is a little hint, it's always going to be your equivalent voltage. So when you see this value here, your power supply, it's your equivalent voltage. So this is why we label it first. So this is coming straight from this. So step number 2 is we need to find our equivalent resistance. So basically what we need to do is we need to add a resistance, and we need to get to our equivalent circuit, right? So like we talked before, we know that resistors add normally. So this is your next important step. We're going to do 10 plus 5 plus 10. Okay, we add all these up together, we're going to get 15. We're going to put that 15 value here for our equivalent resistance. But before we do that, we're going to draw our new circuit, right? So we're going to draw the new circuit. So we add all these up. We get 25. And for your lab reports, you must draw your next circuit, okay? It's very important that we have an understanding of what we're doing. So we add all the resistance up, and what you're seeing here is your equivalent circuit. It's the simplest form of your circuit. That means you just have a simple series circuit, and it has 1 resistor, okay? So we add all these resistors up, and we redraw our equivalent circuit. So now we have 25, and we have our 5 volts. Okay, now step number 3, we have to calculate our equivalent current, okay? So now we're going to calculate our equivalent current, and we're going to use Ohm's law to do that, right? So remember, we have resistance, we have voltage, okay? And now we want to know current. So we're going to use this equation right here. We're going to take our voltage, which is 5 volts, and we're going to divide it by our resistance, which is 25 ohms. We do that, we're going to get this value right here. So now we calculate that, it's going to be 0.20 amps. Okay, now step 4, we're going to use Ohm's law up here. Oh, sorry, I misspelled use, but we're going to use Ohm's law up here, and we're going to calculate the rest of our table, okay? And we're going to do that, I call it the zoom out method. So this is a very simple case, but we're going to look at what we know. So the first thing we know is we're working with a series circuit, and in a series circuit, the current is constant, right? So we calculated the current here. right? So that means if the current is 0.20, we're going to zoom out. So we know that the current here is going to be 0.20 amps, 0.20 amps, 0.20 amps. So we're going to plug that into the table. Okay. Now the next thing we're going to do is we're going to use Ohm's law to calculate the rest of the table. So we know Ohm's law is V equals IR, right? So we're going to do our resistance 10 times our current 20, all right, and so forth for all this table. So we do that, and then we get the rest of the values for the table, okay? So that's how we're going to be calculating these circuits. Now again, the first two circuits are fairly simple. Your last circuit is going to be a little bit more complicated. You're doing a series parallel, but you must draw all your circuits out, and you must simplify all your circuits to the simplest form, right? Right here is not the simplest form. This is a series circuit, and a series circuit is a simple circuit, but it's not your equivalent circuit, so you must draw your equivalent circuit, which is your simplest form. Okay. Now, example 2. Oops, I might have messed up with the graphics. But just like before, example 2, we're going to start off by drawing our drawing our circuit and labeling what we know. So here we have resistor 1, resistor 2, resistor 3, okay? And we're going to label all our resistors, all right? And then we're going to calculate our equivalent resistance. Now, this value shouldn't be here because it's going to be our next step. But this 5 value is going to be our equivalent voltage, okay? So step number 2 is to calculate your equivalent resistance. Now, we do that by adding the resistance in a different way. For a parallel circuit, like I said in the previous slide, we're going to add 1 over a resistance, so it's going to be 1 over 10 plus 1 over 5 plus 1 over 10. Raise that to the negative 1. When we do that, we're going to get this 2.5 ohms, and we're going to plug it in here. Alright, so we're basically doing the same thing that we did for a series circuit, but we're doing it for a parallel circuit, and we're going to have to use different ideas a little bit too, right? So step 3, we're going to calculate our equivalent current, okay? So calculating our equivalent current, we're going to use Ohm's law again, which is I is equal to V over R. So we divide our voltage divided by our R, and when we do that, we're going to get 2. So our current is going to be 2 amps for this example. And then step number 4, we're going to use Ohm's law and what we know about circuits, and we're basically going to zoom out. Okay, well here we're working with a parallel circuit. What do we know about a parallel circuit? Is when you're working with a parallel circuit, your voltage is constant. So we're going to look at this, and we're going to say, okay, our voltage is constant. I know that for a parallel circuit, that's 5, right? So this is 5 volts. So I'm going to zoom out here. And I'm going to say, oh, okay, well, if this is a parallel circuit, that means this has to be 5 volts, this has to be 5 volts, that has to be 5 volts. So we're going to label 5 volts across this. Okay? Once you do that, and I probably should have did the animation differently, you're going to multiply, or you're going to use Ohm's law to calculate your current, right? So you're going to do your voltage, 5, divided by your resistance, 10. 5 divided by 10 equals 0.5. 5 divided by 5 equals 1. 5 divided by 10 equals 0.5. So again, all we're doing is completing this table about what we know. Now again, it's very important that you draw your circuits, right? This is the main thing, because when you get to more complicated circuits, like on the next slide, you'll get lost. I know these two you could probably get by without drawing the circuits. But in order to get credit for this lab, you must draw your circuit. I cannot stress this enough. In order to get credit for the lab, you must draw your circuits like this, okay? So please follow this video. And the reason why it's really good practice, because you will get lost on some of these more complicated circuits, and there's no way that you could actually fill out the table without understanding where things are moving and so forth. So it's very important that we draw these out so I can see that you have an understanding of what you're doing. Okay, now example 3. Now this example is going to be a little bit harder. Okay, so we're going to go to step 1, and we're going to draw our circuit, right? Now this circuit that we have here is known as a series parallel circuit, right? So it's a little bit more complicated. right here I can see that this resistor and this resistor are in series with each other, and that this resistor and this resistor are in parallel. And then all of this, when you look at it as a whole, is in series parallel. So we have a series parallel circuit. So now you might be thinking, what do we do? Well, it's going to be the same thing. We're going to have to calculate our equivalent resistance, okay? But we're going to have to do a few extra steps now. And this is why I stress it's very important to draw your circuits out. Okay, so when I'm looking at this, the first thing I say, and you could go the series approach, you could add these two up, but the first thing I look at is I want to deal with this parallel part because I don't like looking at this parallel part. So you pick a part of your circuit to simplify. So I choose this area to simplify. You could have chose these two, but I'm going to choose this area. So I'm going to say, let's simplify this, and let's add these two resistors up. And remember, since this is in parallel, it's going to be 1 over 10 plus 1 over 5. But let's add these up, and then raise to the -1, of course. And let's redraw our new circuit. So this is what I did. I did 1 over 10 plus 1 over 5, added that up, raised that to the -1, and I found, that I got 3.3 ohms. Okay, so that's the first step. The next step is you have your new circuit, which is now it's all in series, right? Which is good. That's what we wanted. So now we can add these up normally. We're just going to do 10 plus 5 plus 3.3 because this is a series circuit and they add normally. Now you get your equivalent circuit where this is about 18.3 ohms. Now again, over here this is our approximation because I raised it up to the -1, so there may be a small rounding error if you're looking at my numbers and you're calculating it at home. But it should be about 18.3, depending on how you round. Now, this is our simplest equivalent circuit. So now that we have 18.3 ohms, we're going to put that in our table. And just like before, we're going to calculate our equivalent current by using Ohm's law, I equal to V divided by R. And we get that for this circuit, our equivalent current is going to be 0.55 amps. Now again, the last step is the zoom out step. And this is why it's important to draw all your graphs, because as you can see, it's a little bit more complicated. So now we're going to have to ask ourselves, what do we know about the physics of these different types of circuits? So we're going to look at here, and we're going to say, okay, well, I know that the current here is going to be 0.55 amps. Alright, so I'm going to take this knowledge that I learned that this is 0.55 amps, and I'm going to zoom out, and I'm going to look at here. So this is a series circuit, so I know that there's 0.55 amps here, 0.55 amps here, and 0.55 amps there. Okay, so I'm going to write that in my table. 0.55 on 1, 0.55 on 2. Okay, this one is a resistor that we just kind of made up ourselves. Alright, so since we know that this is 0.55 amps, that means we know that in this area it's going to have to be 0.55 amps as well. So we're going to multiply that in, and when we do that, we're going to do 0.55 times 3.3, we're going to get 1.8. Right, so this resistor has 1.8 volts on it. So we're going to zoom that 1.8 volts out, and we're going to take it up here. And we know that this area is in parallel. So for a parallel circuit, okay, we know that the voltage is going to be the same. Alright, so that means that this has to be 0.18 here and 0.18 there. So we're going to plug that into our table. And again, we're going to use Ohm's law to complete the table. Right, so we just do, we use one of Ohm's law's equations to complete this. Alright, and it's the same. So like before, we knew that this was 0.55 when we zoomed out here. Alright, so we labeled 0.55. Then we use Ohm's law to calculate that. Okay, then we use that 0.55 to calculate this pseudo resistor, the one that we made up from redrawing the graph. We got the voltage there, which was 1.8. We know that this area is in parallel, so the 1.8 volts has to be the same here and there. Alright, so we wrote the 1.8 in our table. And then what we did was we used Ohm's law again, because we had this and that, to calculate the unknown. So I call this the zoom in, zoom out approach. Okay, so the first thing we do is we draw the most complicated circuit. The next thing we do is we have to add these up, right? So we added these two things up in such a way, right? So this is parallel, so we added this up so we can have a simple series circuit, and then we added the simple series circuit to get our equivalent circuit, right? Which is our simplest form. And once we got our simplest form, we have to find our equivalent current. So we did that. And then once we got all our equivalent information, we zoom out. And we use that information, particularly the current in this situation, to tell ourselves, oh, we're back in the series circuit. The current's the same across all these resistors. So now I'm going to use Ohm's law to finish the calculations, right? It's because I knew for resistor 1 and resistor 2, they're in series, that the current is the same. So now I'm going to use Ohm's law to calculate the voltage. And then now I have to take into account my pseudo resistor. I'm going to have to use that 0.55 current again to multiply by that 3.3 ohms using Ohm's law to get that 1.8 value. Now I use the principle of the knowledge that I know about a parallel circuit, that the voltage is the same. So I know that it should be 1.8 volts here, 1.8 volts there, right? So I label that in my table, and then I use the fact that I know the resistance and now I know the voltage to calculate, using Ohm's law, the current. Okay, so it's a zoom in, zoom out approach. I know I'm being very repetitive, but circuits is typically very difficult. So please watch and rewatch these videos. But for your lab report, it's very, very important that you draw your circuits out like this. So I know that you have the understanding on how to add these things up, because you have to be able to identify that. If you wanted to, you could add these two resistors up, right, and went a different way about it, but this is the way I did. So you're going to have the exact three same types of circuits, just with different numbers. So if you could understand what I did here, you should be fine in the lab. I tried to give you more than you need for the lab report. Again, if y'all have any questions, please feel free to reach out to me. This is going to be a little bit longer video. But thank you and have a wonderful evening.